engineering. And then we've got a few other things. We've got the buffer overflows, denial of service, information disclosure, and then maybe we might have some time at the end. We'll see. But we're making decent time. As I mentioned, Dan's not here. This really isn't meant to be a sales pitch at all. So if this is something that you guys are interested in having more people in your organization learn about this stuff, I work for National Instruments. I don't sell training or anything like that. Dan's company, however, Dan Group does, and they do a really good job of training. It's something that we use. When I first got my information security program started at National Instruments back about almost a decade ago, we hired Dan Group to come out and do some trainings for us. They did a really, really good job, and then they left us with the slide deck, and we were able to turn it into what's now the program that I go to other countries to train our developers on. So I highly recommend that. Did you have a question?
I work there.
Oh, very good. All right. Do you do training? All right.
Military.
In the military, all right. Yeah, Dan Group is based out of San Antonio, so they're almost local, and they do a lot more with like airports.
Yeah.
Cool. All right, so cross-site request forgery. I briefly mentioned this earlier when I talked about the cross-site scripting and some of the ways we kind of move beyond cross-site scripting into other types of attacks. And this is one of those things. So cross-site scripting occurs, or cross-site request forgery rather, occurs when an application is susceptible to forced background requests from the users. The attacker uses the combination of cross-site scripting vulnerability, which is basically trust in that website, right? You've got that domain there, along with poorly implemented server-side functionality. And so the cross-site scripting payload causes an authenticated browser to make unintended requests. The server-side code then sees that browser making a request. It's got the information as though it's coming from the valid things on the domain, and it processes it just as if it came from the authenticated user. The impact here is moderate. The attacker can trick victims into performing state-changing operations that the victim is authorized to perform. And examples include updating account details, making purchases on behalf of the user, log out, and even log in. Interesting, one of the reasons why you might want to log somebody out, people are like, why would I want to log them out? Because if you log them out, then you can basically force them to have to log back in, and that might be a way to capture their credentials. So here's a little picture example of what we're talking about. In this case, we have a bank. And this banking site, we have a user in their browser, and they log into the banking site. And somewhere along the way, while they're using the banking site, they get distracted. It's probably one of those phishing emails that we were talking about over there. And they click on a link. And that takes them to a malicious site. And that malicious site says, hey, go over here. Go on this banking site, and here's the page that you're supposed to call. And it uses the functionality of that site, and it says, transfer money, which the site says, hey, that's normal, I should be transferring money. And because it does it within the context of the authenticated user, that user's browser that has the session logging thing, it says, yeah, cool. I'll go ahead and make that request to transfer money. And then that bank will go ahead and transfer the money on behalf of the user because it thinks that's the user's browser making the request, when it's actually the malicious site telling the browser to make the request. So just like cross-site scripting, we have a couple different variations here. We can have stored cross-site request forgery, or we can have reflected cross-site request forgery, depending on whether the data is stored in the database, or whether that data is actually part of a parameter. We can also have GET or POST requests and performance. So testing applications, we start out by looking for cross-site scripting flaws. Once we find the cross-site scripting flaws, we've already talked about how we do that. It's pretty easy to automate, request and response pattern, we have tools for that. Once we have the cross-site scripting flaws, we look at the impact. And we say, how much HTML or JavaScript can be injected, and where? What's the context? What's the domain that this runs on? And then we look at how server-side functionality has been implemented. Can our cross-site scripting payload, the JavaScript that we're pushing into this, make requests that would exercise that functionality? Maybe it's calling an API or something like that. And so to craft a CSRF payload, we start with our cross-site scripting payload. We may have to deal with pre and post HTML, just like with cross-site scripting. And the most basic attacks are going to just use a GET request. So the interesting thing about images is that that image source tag can be used to grab data that's not images. Weird, huh? The image tag basically tells the browser, go fetch this thing and then try to render it. Well, if go fetch this thing is what happens first, right? Then it's going to go and grab that thing. So in this case, image source says, hey, server.com, I want to access this resource and I want to pass in this do bad stuff parameter. Now, when the browser accesses server.com, another thing a lot of people don't realize is every request that you make, it's sending along your cookie information. So if you're authenticated to server.com already, and then this site says, hey, go grab this for the image, it doesn't care that it's an image. Your browser doesn't care that it's an image or not. So it just goes to that site and says, I need this resource. And if it's authenticated and that functionality is available to that user, it's going to go ahead and make that request on behalf of the user. Now, image tags aren't the only place where we can do that. We can do JavaScript, so script source equals. That will tell it to make that request on your behalf, and we'll send the cookie on your behalf. Link rel equals style sheet. You can specify a style sheet. That will load that same information. So you're basically using these as ways to make the browser make a request on your behalf. You can also use post requests, but post requests get a little bit more complicated. Because with XHR, XML HTTP request objects, you require a much bigger payload. You're basically saying, here's some JavaScript, and I need to specify this as the post parameters, and I need to specify this as the URL, and here's the method that we're going to use, right? It's a lot more JavaScript. So that's why we say, over here, we say how much HTML or JavaScript can be injected where. If we can't inject a lot of JavaScript, then we're probably going to be stuck at GET requests instead of post. Examples in WebGo to do this is our example. The mitigation here is to protect against the cross-site scripting vulnerabilities. This is, again, why it's really important for us to go and understand those vulnerabilities. And even if it's not something that the user, right, it doesn't affect our server side, it's a user attack. These are pretty big deals if users can have their password changed on them or change their settings, things like that. In order to protect ourselves from cross-site scripting, we learned that we have to positively validate our inputs and we have to encode the outputs. And then the last little bit here is we designed sensitive server-side functionality with protection in mind. So this means preferred inputs and custom requests because they're a little bit harder to pull off. Not that they're impossible, that's harder. And then the real fix for cross-site request forwarding is using a random token with a request. You'll also hear this referred to as a nonce once. By including a random token with a request, you're basically saying that this is a unique identifier for this page from this user. And if they don't provide this, then we don't give them that functionality. So what ends up happening is in our cross-site scripting, cross-site request forgery scenario, that being transferred, the malicious site doesn't know that number. They don't know the number that the user is using in order to access the banking site. And if they don't have that nonce, that random token, then they can't validate that this request is made on behalf of the user, and therefore it fails. If you don't validate that, you don't use that random number, you don't validate that number, then that means that the user can make that request on your behalf, and the attacker can make that request on your behalf. The other piece here is requiring re-authentication for sensitive transactions. And this is the reason why a lot of password change routines basically will require you to enter your old password before you enter the new password, right? Or if you're going to update information in certain platforms, you have to prove that you're that user again before you actually do those things. Even if you have a valid session, right? You may be logged in. because they don't want somebody to be able to exercise a cross-site request filter attack and change that information for you. Or they don't want a user to be able to do like a fire sheet attack, steal the credentials, log in using that, and then change your password. If they don't have your actual password, they're just logging in via the session or something like that, then they can't do that. In terms of post versus get, it's relatively easy to tell a browser to make GET requests versus post requests. We talked about crafting the payload before. Lots of injectable tags cause the browser to make GET requests, right? So that makes it a little bit easier. But that's not enough protection alone. It helps to reduce the exposure. It's part of our defense in depth approach. But there are ways, if we prefer the post to get, there are still ways to attack the application. Talking a little bit more about those random tokens. These are either session or page-specific random tokens that have to be passed with the request. So these are generated using new crypto. Think of those SHA-2 hashes that we talked about earlier. Good randomly generated values that are known only on the server side. So we generate that value for that page or that session on the server side, and then we expect that when requests come in, that those requests have that nonce provided. If they provide the nonce and it matches up, then they're good. They have a valid session. If somebody from outside the site comes in and says, I need to do that same action, but they don't have the value that we're expecting, it's not okay. We don't allow that. So you verify those on the server side. And finer-grained tokens can be more secure, but might be hard to maintain. So in the case here, we have this make transfer servlet. It's a form action. And we have a hidden parameter. And in this case, we have a name, that's a random number, and we have a value, that's a random number. So this is one of those examples where it's going to be hard to maintain because how do you validate on the server side that the parameter name and value are correct when you don't go with what it should be. So it requires a little bit more effort for you to track, hey, I gave this particular user, this particular name, and this value, and is that proper information coming across correct? In terms of required and re-authentication, we want to make this a multi-step process. We want to require the user to represent their credentials, basically confirm that they are who they say they are, and we may even want to use out-of-band facilities to confirm this. So maybe send an email or send a text message, make them click another link to say, yes, I am this person, and yes, I really do want to change my name to Donkey Kong 64. Right? All right. In terms of Java, we kind of talked about these earlier in the cross-site scripting section. We want to do URL encoding, and there's a few different ways to do that. So now I get to tell you about my friend Sammy. Sammy Kamakar, really interesting guy. He's actually, he was one of the guys that I got to speak here at LASCON back in 2010, the first year of the conference. So Sammy did what's called MySpace 1. This is what made him, we won't even say names, influence, right? It was based on assembled JavaScript that was built from simple substrings. It bypassed numerous negative filters against malicious tags, attributes, etc. So remember what David showed about the negative validation versus positive validation, right? MySpace was using negative validation. It relied on the same functionality being served from multiple host names. You had profile.myspace.com and www.myspace.com. And it used a multi-step background combination of GET requests and post requests. So it went kind of like this. When I'm on MySpace, I get a list of friends. I parse out these special post tokens from there, and then I add Sammy as a new friend. Right? And basically what happened, what Sammy created was this work, where in effect, when you went to the page, or to a page, of somebody who was already affected by this MySpace work, it would tell your browser to say, hey, I want to add Sammy as a friend. And then you would add Sammy as a friend on your page. So every single page that a user goes to who's already affected by this, they will then go and add Sammy as a friend. All right? So here's the worm in action. Sammy starts off and says, if I can become their friend, if I can become their hero, then why can't their friends become my friend, my hero? I can propagate the program to their profile, can't I? If someone views my profile and gets this program added to their profile, that means anyone who views their profile also has me a friend and hero. And then anyone who hits those people's profiles has me as a friend and hero. So if 5 people view my profile, that's 5 new friends. And if 5 people view each of their profiles, that's 25 more new friends. And after that, well, that's when things get difficult. The math method. So October 4th, 12:34 in the afternoon, he has 73 friends. Said, I decided to release my little popularity program. I'm going to be famous among my friends. An hour later, at 1:30 a.m., 73 friends and 1 friend request. One of my friend's girlfriends looks at my profile. She's obviously checking me out. I approved her inadvertent friend request to go to bed great. Wakes up 7 hours later at 8:35 in the morning, 74 friends and 221 friend requests. Whoa, I did not expect this much. I'm surprised it even worked. 200 people have been infected in 8 hours. That means I'll have 600 new friends added every day. Wow. An hour later at 9:30 a.m., 74 friends and 480 friend requests. Oh wait, it's exponential, isn't it? Shit. An hour later at 10:30 a.m., 518 friends and 561 friend requests. Oh crap, I'm getting messages from people pissed off that I'm their friend when they didn't add me. I'm also getting emails saying, hey, how the hell did you get onto my MySpace? Not that I mind your hot, from guys, but more girls than guys. This actually isn't so bad, the girls part. 3 hours later at 1:30 in the afternoon, you have 3,503 friends and 6,373 friend requests. I'm canceling my account. This has gotten out of control. People are messaging me saying they reported me for hacking them due to my name being in their heroes list. Man, I rock. Back to my worries. People are also emailing me telling me they're IM natives so that I'll chat with them. Cool. Back to my worries. Apparently people are getting pissed because they delete me from their friends list, use someone else's page, or even their own and get reinfected immediately with me. I rule. I hope no one sues me. 5 hours later, 6:20 p.m., I typically go to my profile to view the friend requests. 2,503 friends, 917,084 friend requests. I refresh 3 seconds later, 918,268. 3 seconds later, 919,664. A few minutes later, I refresh 1,005,831. It's official, I'm popular. I've hit 1 million plus users in less than 20 hours. I've hit over 1/35 of all MySpace users. Every request is from a unique, living, and logging user. I refresh once more and now see nothing but a message that my profile is down for maintenance. I messed up, didn't I? I'm now more afraid and decide I'm never doing anything near illegal ever again. True, so there's been a few other things since then. He was, I think, last Black Hat or the time before, he was doing car hacking. Before that was like some drone stuff he was doing. To get my mind off everything, I've given downloading a copy of the latest nip covenants. An hour later, 7:05 p.m., a friend tells me that they can't see their profile, or anyone else's profile, or any bulletin boards, or any groups, or their friends' requests, or their friends. Nothing on MySpace works. Messages are everywhere saying that MySpace is down for maintenance, and that the entire MySpace crew is there working on it. I ponder whether I should drive over their office and apologize. Another attempt to free my mind of worry, and go back to watching some episodes of the OC, which I downloaded a few days earlier. I'll share the rocks. 2.5 hours later, 9:30 p.m., I'm told that everything on MySpace seems to be working again. My girlfriend's profile, along with many, many others, still say Sammy is my hero. However, this actual self-propagating program is gone. I'm relieved that it's back up, as they can't claim damages for any downtime past the second if everything is in fact working properly. 10 minutes later at 9:40 p.m., I haven't heard from anyone at MySpace or Fox. A few minutes later, my girlfriend calls, I pick up, and she says to me, "You're my hero." Don't actually get it until about 3 hours later. All right, so that's the MySpace one. And Sam used cross-site scripting, he used cross-site request forgery, created this worm, and the result of it was, well, he took MySpace. Right? MySpace World in action, kind of see different pieces of it. Probably too small to really show anything. Lessons learned from MySpace here. First, better input validation, right? We should be looking at positive filters versus negative wherever possible. Interpretable HTML is a really big place, right? So carving out a couple of tabs saying, hey, we can't do this thing, we can't do this thing, or syntax bits, they don't remove the ability of attackers to find a workaround. Attackers are smart, they're going to look for ways to bypass that. So if we do positive filtering and we say, these are the things that we allow, that's going to significantly reduce the attack surface than possible, and it's going to restrict what an attacker can do. Secondly, be careful about what functionality is available from where. Prefer those post requests to the GET requests. What applications are available to the given host name, right? Not have the same application across multiple hosts. And then we want to, this is similar, be checking to be sure that HTTPS content is now available via HTTP. So to recap here, cross-site request forwarding vulnerabilities allow attackers to force a user's browser to undertake actions that they don't want for you to know about. There's multiple varieties, including stored and reflected, get, and post. And to guard against it, eliminate our cross-site scripting vulnerabilities, prefer post to get, and then really the only true way to eliminate it is to use nonces or random tokens to address the issue. Make sense? Questions? Sammy is all our hero. Super nice guy. You guys are probably wondering what happened to Sammy. Sammy had a bunch of federal agents kicking his door early in the morning at gunpoint. He got taken off to jail, had to explain the whole thing. I believe he was not able to access a computer for something like 2 or 3 years. Promised not to do anything else like that again. And Sammy's still very active now. If you've ever heard of the website Fiverr, that actually was Sammy's website. And then he's been a lot at stuff since then. So, interesting guy. All right. Normally when we do this class, Dan and I are bumping back and forth. You can tell my voice is feeling. All right. So moving on from here. Oh, some stuff. CSRF Guard is a defense tool that you can potentially use for your application, where it will generate those nonces for you and validate them for you. Yeah. So number 9 of our 10, using components with known vulnerabilities. Components such as libraries, frameworks, and other software modules almost always run with full privileges. So if a vulnerable component is exploited, an attack can facilitate serious data loss or server takeover. So applications using components with known vulnerabilities can undermine application defenses and enable a range of possible attacks and impacts. Impact here is moderate. I feel like I should just get rid of these impact slides because it's like everything is moderate, everything is moderate. It all depends on what the business of the data, blah, blah, right? It's always the same thing. So it really just depends on what the net effect of this is. You know, is this injection, broken access control, cross expertise, whatever. It could be from, hey, we just got some data, all the way to complete post takeover and data compromise. And we want to consider what each vulnerability might mean for the business control by the affected application. So how would we tell if we're vulnerable to component with known vulnerabilities? This is really a matter of getting the right data. And so in order to figure out if you're vulnerable, you have to search databases, you have to be on mailing lists, and you have to be looking for that data. So if I run, I talked about Google Web Toolkit the other day, or earlier, I want to be on the Google Web Toolkit mailing list, because they're going to tell me when a new version comes out, and they're going to say, there's these vulnerabilities in the old version that we just fixed. If I'm not doing that diligence, then I don't know. And this goes with applications, it goes with servers. You know, if Red Hat comes out with a new release, you want to know about that, because you want to know what vulnerabilities they fixed. Or, you know, if you have Cisco equipment and they come out with a new iOS, you want to know what they're fixing. If one of your components does have a vulnerability, you need to evaluate whether you're actually vulnerable. So you need to check your code and see if it uses the part of the component with the vulnerability and whether that fault could result in an impact to care about. So a lot of times when somebody says this application is vulnerable to vulnerability X, you look at vulnerability X and you say, well, that vulnerability X is in so-and-so function. And none of my code ever calls that particular function. So am I vulnerable? Not unless somebody ever rewrites the code to call that function, right? But if I do, then I'm definitely vulnerable. Or maybe it's under certain conditions. Maybe I call that function, you know, in an admin capacity. I'm an admin user who that admin user makes a call that function. So now I'm scoping it to, hey, it's only admin users that are affected by this. And I don't have to worry about anything else. So these are the kind of things that we use to determine how big of a deal is this. What's the impact going to be to our environment? An example scenario. So component vulnerabilities can cause almost any type of risk management. That could be from trivial to sophisticated malware designed to target a specific organization. Components almost always run with full privilege of the application, so flaws in any particular component can be serious. These two components were downloaded 22 million times in 2011. There's Apache CXF, there was an authentication bypass flaw in there, where by failing to provide an identity token, attackers could invoke any web service with full permission. Read that. There's a Spring remote code execution. Use of expression language implementation in Spring allowed attackers to execute arbitrary code, effectively taking over the server. So if you weren't looking and you had implemented Apache CXF or Spring about the time that these vulnerabilities were there, and you hadn't upgraded them, then each application that you have that's built on top of those frameworks now has that vulnerability built in. So how do we prevent this? Most component projects don't create vulnerability patches for old versions. Instead, they just fix the problem in the next version. And this is why upgrading to the new version is critical. And I don't think it's in here, but there's actually a tool from OWASP called OWASP Dependency Check. And I think it's Java only, if I remember right. But it's a tool that was specifically created for this purpose. It looks at your application and says, here's all the dependencies for your application, and based on those dependencies, you know, here's the versions that you have, and these things are vulnerable. So that's one example, and a lot of these new IAST kind of tools, interactive application security testing, a lot of these tools are starting to build in this kind of functionality, where they're able to detect what frameworks you're using and the versions of those frameworks. And they're able to say, hey, based on this particular framework that you're using, this is out of date and it's got these vulnerabilities. So we're starting to see more and more tools pop up to help us manage these issues. Software projects should have these things in place. So you should be able to identify all components and the versions you're using, including all dependencies. When we create an application, here's the things that make up this, and here's the versions. Second, we want to monitor the security of those components in public databases, project anonymous, and security anonymous, and keep them up to date. So we want to understand every time a new version comes out, what the impact is to us. Third, we want to establish security policies that govern the use of those components. So anytime somebody wants to bring in a new platform or something like that, we define as security practitioners if that's acceptable to them. And part of that is somebody has to say, yes, I will own Google Web Toolkit, and I will track when new versions come out, and I will make sure that my software gets updated every time Google Web Toolkit gets updated. Because if we don't do that, then we've introduced a new vulnerability into our environment. And lastly here, where appropriate, consider adding security wrappers around components to disable unused functionality or secure weak or vulnerable aspects of the component. So maybe we have to use this library. Maybe there's no other option. This is the only library that does what we need to do. And maybe there's function calls in there that we really don't want to expose. We can write a wrapper that basically calls that functionality, but does not call the effective functionality. And we can use that to basically isolate it while still utilizing that actual library. Questions about that? Right. For wrappers, I don't think that there's anything in here for that. Wrappers are kind of subjective, I guess. So it's more about understanding how the application works, and then you're basically writing an application on top of that application. I can give you an example. So with simple risk, one of the things that I did is I wanted to be able to enable CVE lookups in simple risk, where you basically enter a CVE, it'll go and grab the information and pull it into there. And to do that, I actually leveraged what's it called? Tools Watch. I don't remember the name of the actual tool route. BFeed. So BFeed is a vulnerability database. And it's got a lot of functionality in there, and I think he's even started writing some kind of API kind of functionality there. But it's written in Python. And my simple stuff is written in PHP. And I didn't want to expose the entire array of functionality in that. I only wanted to be able to say, here's a CD, give me the data. So what I did is I wrote a wrapper on top of it. And so when somebody calls that functionality, the only thing they can call is give me this CVE, right? And then the only thing that it returns, get CVE, basically calls into that, calls the BFeed and says, hey, I need the information. BFeed hands it back, and then it returns the JSON result. So it's that kind of thing that we're actually doing. There's lots of other functionality that he's built into BFeed. You know, there's CWEs and all this other stuff. I didn't want to expose any of that. I wrote a wrapper to basically strip all that out, so it's the one little bit of functionality that I wanted. All right, so to recap here, this happens when applications use components with no vulnerabilities, may undermine application defenses, enable a range of possible attacks and impacts, and can be prevented by identifying components and versions you're using and establishing processes to monitor their security and update when necessary. And it looks like we do have OWASP dependency checking here. Java libraries are there. There's something called safety git for .NET libraries. And then there's OWASP good component practices project. If you're interested in finding out more. I don't see anything in there specifically about wrappers. All right, moving on. Last one of the OWASP top 10, unvalidated redirects and forwards. Applications frequently redirect users to other pages or internal forwards in a similar manner. And sometimes the target page is specified in a parameter as part of the URL, which allows the attacker to choose the destination page. The attacker can link to an unvalidated redirect and we trick the victim into clicking it. And this is basically preying on the user's trust of that domain name in order to transfer them to another site. Because they think, if I go to www.ni.com, I trust ni.com. And again, it might even have that HTTPS in front of it, and I trust HTTPS. But if the redirect there says, and as soon as a user hits this redirect, I'm going to move them over to this other site, right? The user is going to click the link because they see the www.ni.com. So the attacker is going to target unsafe forwards to bypass security checks to basically make users think that it's an acceptable site. That's okay for them to go there. So the impact here is moderate. Some redirects may attempt to install malware, trick victims into explosive passwords or other sensitive information. And unsafe forwards may allow access control bypass. So we consider the business value of retaining our users' trust. The trust is critical. I don't know about you guys, but I like our users. Our users spend money on our website, and so I'd like to retain their trust. So am I vulnerable? The best way to find out if an application has any unvalidated redirects or forwards is to first review the code for all users of redirects or forwards. And for each use, we want to look at the target URL is included in any parameter increments. And if a target is in a parameter value, then we check to see if that's actually validated. And if it's not validated to contain to only allow destination or some element of destination, then we probably have an unvalidated redirect. Also, we can spider the site. Because in addition to parameter base, we might also see 300 response fields. Typically a 302, 301, something like that is going to be a redirect. And so if there's parameters that get supplied to our page before we see those 302 redirects, then that parameter might be a target URL that we are then redirecting to page 2. And if it is, then we could try changing that target, seeing if it goes someplace else. And lastly, if code is unavailable, let's just feed data into the parameters and look at them. If it's going to somethingelse.com, or it's going to page.htm or whatever, change that value. Change it to something else and see if it goes someplace else. So here's an example. We have an application, it's got a page called redirect.jsp. It takes a single parameter named URL. And in this case, we're supposed to go to example.com/redirect.jsp, URL equals whatever. Right? But our attacker says, I don't want to go to whatever. I want to go to evil.com. And then sends out a phishing campaign and sends it out to a bunch of people and says, hey, you guys trust www.example.com. You guys know that's a site. You guys go there all the time. Maybe they post in the forums on example.com, hey, this is the new, sign up here for a free whiz-bang, right? And as soon as the user clicks the link, it's going to redirect them to evil.com. And then whatever evil.com is supposed to do, maybe it says, oh, enter your information to win the whiz-bang. Okay? They don't even look at the URL up top. They enter their information. Or maybe it's something where it detects if you have Flash installed, it runs a Flash exploit. Second scenario, you may have an application that uses a forward to route request between different parts of the site. And to facilitate this, some pages use a parameter to indicate where the user should be sent if a transaction is successful. And in this case, the attacker crafts a URL that will pass the application's access control check, and then forward the attacker to an administrative function that they would not normally be able to access. So in this case, we see boring.jsp forward equals admin.jsp. So the attacker is leveraging this other functionality in order to access an admin page that they wouldn't normally have access to. So how do I prevent this? Safe use of redirects and forwards can be done in a number of ways. First, don't do it, right? If you can avoid using redirects and forwards, you absolutely should, because very little good is going to come out of it. That said, there are certainly situations where you can't avoid it. And if you have to do it, don't involve user parameters in calculating where to go. Right? So don't say, user said I should go here, therefore I'm going to redirect you to here. Right? That's trusting the user. And if we've learned anything today, it's don't trust users. Users are bad. Users can do bad things. Right? Trust but verify. All right. So the third thing, if we absolutely cannot avoid using redirects and forwards, and we can't not involve user parameters, we have to get the data from the user, then we have to look and make sure that the value that's applied is valid and authorized for that user. So we look at the data that comes in, and we say, is this someplace the user should be going? And maybe that's a matter of verifying that the domain is correct. And maybe it's saying, hey, we're on www.example.com, and I want to make sure that this redirect is going to www.example.com, and if it's not, I will redirect it. But we need to validate that. It's also recommended that if you have to do a parameter value like that for a destination, it should be a mapping value rather than an actual URL or portion of URL. What this means is you say redirect equals 1, and 1 is this domain, right, or this site. And 2 is this, and that's this guy. And by doing that, we're able to positively validate our inputs. We're able to say, here's the proper range that we expect for the proper data. And if it's not one of these things, don't go there. Right? So this way, we're able to leverage server-side functionality in order to translate it and say, oh, you meant to go to this page. Applications can use a SAPI, that verifies security API, to override the send and redirect method and make sure all redirect destinations are safe. And you should, avoiding these flaws is really important because they're a good target for phishers. You try to gain the user's trust as a result of the proper metadata, the SSL certificates, things like that. Questions about that? I've got some really good examples of this one that I love to use in my class, but I can't share those things with you guys because they're nice. All right, so recap. This happens when an application redirects the user to another page using an unvalidated parameter, utilizes a familiar URL, trick the user, bypass security checks, might install malware, trick the user into disclosing passwords for other sensitive information. To find it, we check for unvalidated parameters in the redirect code, and to prevent invalidated or revert parameters. Cool. So with that, we've gone through all of the OWASP top 10. You guys know the OWASP top 10 parts. Next year, you guys are going to teach this class. I'm going to just kick back there, right? But you guys at least now know what you should be looking at. I think the majority in this room raised their hands and said, I'm a developer. And hopefully that means that when you guys are going through and you write your code, you will notice these patterns. You'll say, hey, I'm taking that user output and I'm echoing it back into the page, and that's a cross-site script condition. I shouldn't do that, right? Hopefully you'll do that. And maybe you'll see another developer, and you'll be looking over their shoulder and be like, oh, where are you doing that cross-site scripting, right? So, there are a few other prominent issues that I want to talk about that are not in the OWASP. And some of these are kind of going away, like buffer overflows, for example. Most newer languages are actually handling the buffers for you, which means that they're not as common. But there are still languages like C and C++ where you have to do your own buffers. And the result of that is that you have potential for buffer overflow. And we still, every once in a while, will see CVEs for buffer overflow vulnerabilities. So it's not bad. Buffer overflows occur when input is larger than an application expects, and it gets put into a buffer that's the size that we expected. The input then overruns the allocated space and overrides memory that it really shouldn't have access to. So if you think about memory as like one big continuous block of space, right? When we want to put something into memory, we allocate what's called a buffer, which is the space of memory that we expect to use for our application. In modern languages like Java, for example, they kind of guess at how much memory should be allocated. If it needs more memory, it'll allocate more memory. So it handles this thing for us, and we don't have to worry about that. But some more, we'll say, archaic languages, like a C++, don't do that. So when you allocate space in memory, you say, in this case, I want 6 bits of data or 6 bytes of data of memory there. So if you look in that second picture, we've allocated a buffer of size 6, and we've taken our data, which is of size 4, and we stuck it into it. And our data fit, and there wasn't a problem. If we take that same buffer of size 6, and we now put malicious data into there, or malicious code, that malicious code is bigger than the buffer that we've allocated for it. And so what you see is what's called a buffer overflow. We have overflowed our buffer, and there's now data that's written into memory that we didn't allocate. Well, that data that's going into memory that we didn't allocate, that's still memory. It's overwriting things that are sitting in memory. It's overwriting the stuff that's outside of our buffer. And if we can write to the right places, we can actually take control of what's called the instruction pointer, which is basically the pointer that says, here's the next instruction to run. And we can actually write our own instructions. So the net result of the buffer overflow is we now have the machine running our code instead of the code that the machine thought was supposed to run, simply by controlling where stuff goes in memory. Now, newer operating systems have implemented safeguards against this. They do things like, it's called ASLR, address space layout randomization, where instead of memory basically being one contiguous flow, it's like here's some data, and here's some data, and here's some data, it's all randomized. Right? So there are some controls in place to try and prevent the exploitation of buffer overflows. But you're still, in situations like that, you're probably going to cause a denial of service condition. Because you're going to write to memory, you just don't know where in memory to write. And the net result is eventually there's going to be a weird instruction, and the system's probably going to lose it. So here's an example of a buffer overflow. In this case, we've created a name buffer. That name buffer is size 10 characters. And then we print to the screen, enter your name. And then that getS function is get string. This is a C routine. And it says get the string and stick into the name buffer. So in this case, if we enter when it says getS, if we put something like really, really big name into that buffer, and it's size 10, we've now overflowed our buffer. Now the way to make this more secure is to use what's called the getS function. So this is a function that's implemented by C, and if you know it, you're going to use it. If you don't, you're probably going to use getS and get it wrong. But getS says specify the name, specify the size, and specify where the data is coming from. And this limits the size of the input that's allowed to be copied into the name buffer. So as somebody's inputting the data, you bound the data input to the buffer that we're storing it, and it will not allow you to put more data in the buffer than the buffer that we allocated. And that's the benefit of using getS instead of getS. Make sense? It's not a yes. So implications here. By careful manipulation of the payload, malicious user can control that instruction pointer, the thing that says this is the next instruction to run, and runs arbitrary code of their choosing. And as I mentioned, even with less sophisticated payloads or things like ASLR to mess this up, you still can cause crashes. And we talked earlier, one of the very first things I said is CIA, confidentiality, integrity, and availability. Well, denial of service is an attack on the availability of our application. And so if we have a buffer overflow, even if we can't get it to run our own commands, if we can cause that system to crash, right, it's a win. At least from the attacker standpoint, from our standpoint as defenders, it's a big help, right? So mitigations here, as I mentioned, most web development environments don't have a lot of fear for it. Java, Perl, C#, VB.NET, VBScript, they all have balance checking at the language level. And that's really nice because it means that we don't have to think about that. We don't have to deal with the buffer piece. But there are still a few applications out there that are built in C and C++. And for those ones, we need to make sure that we're using safe array and string handling routines so that the buffers that were allocated are the right size for the data that's going in. The other thing that we can do here is if we have things that are array, we mentioned this a little bit earlier, is you can use wrappers. And you can wrap these objects and other potentially unsafe code in wrappers and force the input validation of cleansing that we want to make sure it has. So it's going to say, hey, this value should never be longer than this because that's the size of the buffer that we're doing, and then it passes it into there. So the next one up is denial of service. Denial of service, we want to look for situations where attackers can use a lot of your resources with a minimum commitment of theirs. And so things to watch are like login routines, where we mentioned earlier like the scrypt and decrypt functions, where we're running like 15x hash over a certain value. That's resource intensive. For like a legit reason, we want it to be resource intensive because we don't want everybody to be able to calculate those. But if I run a login routine over and over and over and over again, I'm tying up CPU resources for that. And crypto isn't cheap. When I first started messing with the Simport stuff, and I had one of these routines on there, I was like, that would be awesome. I'll just put it on a Raspberry Pi and let's ship that out to customers, right? It would be great. Simport runs awesome on the Raspberry Pi. The place where it doesn't work is the login routine. As soon as you enter that password, the Raspberry Pi goes, thinking, crunching numbers. And it takes like a minute to log in because it's just not powerful enough to do all that hashing that's required for it to have the proper security and credentials. So login routines are very resource intensive. XML processing, I actually saw an interesting talk when I was in Costa Rica at the OWASP chapter there, where they were talking about regex actually. And they were saying that you could do effectively regex dumps, where if you had the right regular expression, it basically is like a wild card in and of itself, and it causes effectively an infinite loop over the regular expression, and it basically ties up all the resources while it's doing this infinite loop. XML, very similar. You can do XML processing, going through a big XML document, take a lot of time, a lot of resources to verify it. You can also do DOM injection, and then logging routines. So every time I log into an application, it logs a whole bunch of information. It's writing the information either to the database, which ties up database resources, or to disk, which ties up disk resources. So if I find a thing that logs a lot of information over a very short period of time, that might be all I need in order to create a denial of service. That's a blank page for an example. That's awesome. Yeah. Actually, I'll give you an example. I used to work for a company called Neopost Loop One. It's owned by a French company, and they did group postage stuff. And they had this MySQL database. And the MySQL database, there was a report that would basically run, customers could basically click to run it, and every time it ran, it would basically run this very, I think it's down here. Test test. It would run this very resource-intensive MySQL query that could take 60 seconds to run. And these run like really big database machines. Like they weren't underpowered at all. It was just a huge query. Well, what would happen is this was just a submit button. It's like a run this request on a page for the customer to access to. You know users, right? When a user gets frustrated with something, what do they do? If it's not coming up fast enough, yeah, they click it again. And if it's not coming up still, they click it again. And if it's still not coming up, they click it again and again and again. So what happened in this particular situation is exactly that. The user found that it wasn't running fast enough, and so they thought it was like the button in the elevator. Like the more times they click it, the faster the doors get closed. That's what they did. Well, the reality of that is every time they click the button, Apache spawns a new process, which creates another connection to the database, which uses up more database resources. So now instead of the database crunching one really bad SQL query, it's now crunching every time they click the button really bad SQL queries. And eventually the database gets to the point where it goes, I can't do anything else, and it tips over, right? So the fix for this these people are awesome. The fix for this particular vulnerability was they put a screen blocker on the page. So when you click the button, it goes loading, 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 right? and it waits until the page is loaded, and then it's like, here's your data. So it doesn't allow them to click the button again, it only allows them to click the button once, and then it tells them it's loaded. Which is good from a customer perspective, because they know it's doing something in the background, and they can't click it again. From an attacker perspective, if I really want to take that database down, like I can open up multiple tabs with that thing, and click load, and then open up another tab and click load and whatnot. So it didn't really fix that vulnerability, but it fixed the issue with the customer clicking multiple times. All right, so on to the information leakage and proper error handling. This is really, really common across different applications. It occurs when applications provide too much information to attackers, and it can be a result of failing to track error conditions. So it may result in accepting stack traces, missing file paths, things like that. It can be a result of verbose application messages providing attackers with information they shouldn't have. So the example here is you have an authentication routine. And if I enter a username into this login form, and that username is not valid, the login form returns an invalid username. And I go and I enter another username and it says invalid, and I go and I enter another one and it now no longer says invalid username, it says invalid password. What have I learned? The username's good, absolutely. So as an attacker, what I'm going to try and do is I'm going to try and figure out what's the valid username, and then I just brute force the password. So this is an example where that username or that error message is giving us way too much information, enough information to carry out an attack. So the way that we fix this is we give them a less verbose error message. We say something like invalid username or password. Right? It's a little less helpful from the user perspective, but from the security perspective, we've given them very little to go off of to conduct an attack. Right? They can't say this is a valid username. You'll see things like this also in like forgotten password features, right? Where you go and you put forgotten password and you'll enter your email address and be like, yep, that's a valid email address. The email's on its way, right? Instead of an email has been sent if the user exists. Impact for information leakage. The attacker learns about controls in the system and can use it to wage additional attacks. So it might be a direct attack against the system, or if I'm getting information about host names, operating systems, paths, files, things like that, that might be something that I use for a social engineering attack. I'll call up the service desk and be like, hey, this is Joe in accounting. The so-and-so server is performing really weird. I tried to look at the file in so-and-so path, but it wasn't coming up. Can you help me with that? Yeah, something like that. Unhandled exceptions sent back to the browser contain things like exception messages, stack traces, file names, other path information, things like that. And the application may provide a reasoning or justification for a response to it. So how do we test this? We send unexpected input to the system, and we look for error messages back. And so this process of sending data in and getting data back is called fuzzing. And there's lots of tools out there, free tools. OWASP does a good job of this. There's lots of different things that you can use that are fuzzers. And basically what it does is it says, hey, we've got this field equals, right? And we'll just send random data into there. It might be empty strings, it might be long strings, it might be strings with special characters, and we'll just see what comes back. And by sending in data that the application doesn't expect, we're able to see how the application performs under all the different conditions. And if we see information that we don't expect, like all of a sudden we see a response that is not the same as all the other responses that we've seen, that could be an indication that there's a problem. All right. Mitigations for this. Don't allow users to see or post error messages. Be careful logging error conditions, and be careful what information you provide to others. In terms of logging and reporting error conditions, it's important for security operations personnel. Right? The first thing somebody asks when we've been hacked is, can I see your logs? I want to know what's happening on the system. They're also useful for debugging issues and things like that. The problem is if your logging routines allow for user injection into the logs, so if I take like a particular parameter and I then insert that into the logs, that can create problems. And so as an example, if I include the end of file character, and that gets inserted into the log based on some data that I send in, when somebody looks at that log, it's going to look like the log stops there. When in fact, I've done a lot of stuff after that, after I inserted that end of file character. So additional characters might be escape characters or things like that. So we want to be very careful, and even our logging routines, we need to make sure that we're properly inspecting the data and sanitizing. And we also talked about in the DOS area, logging can be an expensive operation. If it's an expensive operation, that could lead us to the denial of service attack. Another one might be 3404, so error pages, right? If every page sends an email to the site administrator, that could be a problem. I'll give you an example. In my early days of doing AppSec and NI, we had this tool called IBM LASCON. And I pointed this at the website. And one of the things that it does is it goes and tests for a bunch of like backup pages and backup files and paths of all sorts of stuff. It checks to see if all these things exist. And the net result is if those things don't exist, then it creates 404 pages. And on NI.com, we had something where when you had a 404 page, it would basically submit that into what we call the web request queue, which was a queue that somebody had to actually look at to say, yes, that's valid, hey, we need somebody to fix this, or no, it's not valid, you delete it. Well, AppScan did this 10,000 times, submit 10,000 requests into this web request system, and some poor person, not me, had to go through the system and actually manually delete every single one of those entries. So, in that case, it was a people loss, right? Some poor person did all this, but still not very good. Something that you can consider in terms of error conditions, consider logging into a database with a unique identifier. And then when you present this error to a user, you present a message like, an error has occurred. If this error persists, please contact support and reference error number 1, right? And what that does is, if that's an attacker, they have zero information about it. All they know is that there's an error, and I have this ID. If it's a customer, they call support, they give them the message, and support's able to help them with that because they have access to the database, and they can get the real error that's associated with that error number. Right? So if this is a random value, then the attacker has no idea what's going on, and they can't reach support. But our real support can actually provide them with useful information, to get them fixed up, whatever. So random value. And then the final note here is anyone who communicates with users should be wary of social engineering attacks, right? Social engineering, very, very common these days. I think my team is handling, I would say we're probably averaging 1 social engineering attack per day, at least. And that's, users getting phishing emails, that's people getting phone calls, all these different things. You should have people in your organization trained to identify when this happens and to know how to respond when it does so that they don't fall victim to those types of attacks. Questions about that? All right. It is 3:40 right now. We're going to be getting into the elements of secure design. This is where we start talking about some crypto and some things like that. It also makes for a really good point for us to take a little break. So it's 3:41-ish. Let's go until 3:50. And then we'll come back and we'll finish off some of this stuff. Cool.